We will now look at some numerical integration techniques of converting a continuous system to a discrete one. So let us consider a transfer function h of s. So h of s is equals to u of s over e of s, and let's say it's given as a over s plus I. So the first thing that we need to do is convert the transfer function into a differential equation form, and I can show you how this is done. So we are given a transfer function h of s, which is equals to u of s over e of s, and that is equals to a over s plus I. So to convert this into a differential equation form, can multiply s plus I to u of s. So we'll get s times u of s plus a times u of s equal to multiply e of s this side, we'll get I times e of s. Now we can do inverse Laplace, and in doing so we get u dot of t plus I times u of t is equals to I times e of t. So u dot is u dot plus I u is equal to I e. Now we can take a discrete form of this, where t, instead of t, we can replace it with kt, where k is the sample number and capital T is the sampling period. So we will get u of k times t plus I times u of k times t equal to I times e of k times t. So that's how we got this equation. Now there are several ways in which we can numerically integrate to get u of t or u of kt, and these methods are forward rectangular rule, backward rectangular rule, and trapezoidal rule. So we'll start with forward rectangular rule, which is Euler's rule, but let me just start off with a much simpler system than this. Let's say instead of I over s plus I have a system u of s over e of s, which is equals to 1 over s. U of s over e of s is equals to 1 over s. So the first thing that we need to do is convert this into a differential equation form. So I have s times u of s is equals to e of s. Then apply inverse Laplace. So I'll get u dot of t is equals to e of t. And so basically this is equivalent to u dot of k times t in discrete form is equal to e of k times t. Now to solve for u, what I need to do is integrate both sides. So if we integrate both sides, I will get u of k t is equals to integral, let me say e of tau d tau, where tau is from 0 to k t. So this is how we can get u of kt, and please note that in place of u of kt we can simply write u of k, and that would mean the same thing to simplify the notation. So this integral problem can be divided into two parts, where we first have an integral from 0 to k t minus t, and this is same as integral from 0 to k minus 1 of e of tau d tau plus integral from k t minus t to k t e of tau d tau. So the first part here will simply become u of kt minus t, or u of k minus 1. And the reason for that is, if we substitute in this equation, if we substitute, let's say in place of kt, if we substitute kt minus t, then it becomes integral from 0 to kt minus t e of tau dt. It's same as integral from 0 to kt minus t e of tau d tau. So basically this quantity is same as e of k minus 1. The second quantity is an approximation. So this is where the numerical approximation comes in. So consider, let's say we have a function e. So integral from kt minus t to kt of function e is basically trying to find the area under the curve of e. So let's say we have a function e, and what we are interested in is finding the area from kt minus t to kt, and this is equivalent to k minus 1 to k. So the way we approximate the area is by taking the value of e at kt minus t and just taking it forward and making a rectangle. So what we are doing is using the value e of kt minus t, we are creating a rectangle. So to approximate the area under the curve e from kt minus t to kt, we are just considering this area. So this is going to give us an approximation which is not exactly equal to the area under the curve. And we know that the time interval between kt minus t to kt is t, which is the sampling period. Now this is how we can approximate the area. So it's much easier to find the area of a rectangle than finding the area of under this curve, which we do not know. So basically this problem just comes down to finding the area of a rectangle, and this is known as forward rectangular rule or Euler's rule. So to find the area is given as A is equals to length times width. So the width is basically t, and the height is e of kt minus t. So height is e of kt minus t. And if we simplify this, this is similar to t times e of k minus 1. So if we bring that here, we add t times e of k minus 1, So now u of k is equal to u of k minus 1 plus t times e of k minus 1. So in terms of k, this is our equation. Now we can convert this or apply z transforms and convert this in terms of z. So my u of z, so this capital U will be equal to u of k minus 1 is similar to z inverse u of z plus t e of k minus 1 is z inverse e of z. Now to find u of z over e of z, this is simply rearranging this. So what we get is t times z inverse over 1 minus z inverse, and this is equal to t over z minus 1. Now if we compare this equation in terms of z to this equation in terms of u, so u is equals to, or u of s is over e of s is equals to 1 over s, but my u of z over e of z, which we derived using the fourth rectangular rule, as t over z minus 1. So we can say that t over z minus 1 is equivalent to 1 over s. So we can say that 1 over s is equivalent to t over z minus 1. So basically s is equivalent to z minus 1 divided by t, where t is the sampling period. So this is how we get s equivalent to z minus 1 over t. So now in our equation, in place of s, we can substitute z minus 1 over t, and we expect to get an equation in terms of z. So we have converted our continuous system into a discrete one using fourth rectangular rule. So this is one of the numerical approximation methods. Now if I go back to my notes, you can see the same result that we have got here. So t over z minus 1 is equivalent to 1 over s. So this is how we get that. Now let us look at a different approximation method, which is backward rectangular rule. So the only difference in backward rectangular rule is the way we approximate the area under the curve, as I have shown you previously. So if I go to my whiteboard, so over here we use fourth rectangular rule. So instead of fourth rectangular rule, we are going to use backward rectangular rule to approximate the area under the curve. So to approximate the area from kt minus t to kt, where kt minus t is same as k minus 1 and kt is just k, and the time difference between kt minus t and kt is t. So in backward rectangular rule, what happens is that the value of e at kt is used to make the rectangle. So the value of e at kt is at this point. So from this point, a rectangle is made, and it goes like this. So now to approximate the area under the curve, we are going to find the area of this rectangle. Now again, this is an approximation method and it's not going to give you the exact area under the curve. But if t is very small, then the approximation is very close to the exact area. So to compute this area, the equation is width times height. So the width is t and height is e of kt, and this is also equal to t times e of k, similar to that. So now we bring this into our equation here. So u of k is equal to u of k minus 1 plus t times e of k. And let's apply z transforms to get it in the z form. So u of k will be equal to capital U of z, u of k minus 1, z inverse times u of z plus t times e of z. Now u of z divided by e of z will be t over 1 minus z inverse, and this is equal to t z divided by z minus 1. So now 1 over s is equivalent to tz divided by z minus 1. So 1 over s is equivalent to tz divided by z minus 1, and so therefore s will be equivalent to z minus 1 over tz. So to get from a continuous domain u of s over e of s to discrete domain or digital domain u of z over e of z, we can substitute in place of s z minus 1 over t z, and that will give us uh, the continuous system in discrete form. And if we go back to our notes, we can see that 1 over s is equivalent to tz over z minus 1. Let's look at the last one, which is the trapezoidal rule. And let's go back to my whiteboard. So again, in trapezoidal rule, the way the area under the curve is approximated is different. So let's erase this and let's see how the trapezoidal rule will work. Let's say this is the curve once again, and we want to find the area from kt minus t to kt, and kt minus t is same as k minus 1, and the time difference is basically t, which is the sampling period. Now in trapezoidal, what we are going to do is we are going to form a trapezoid between these two intervals kt minus t and kt, and so a trapezoid looks like this. So we are going to take a line, join it from e of kt minus t to e of kt, So this will be a straight line, although the function e can be something different. It does not need to be linear, it can be anything. And so now this forms a trapezoid, and the area under the trapezoid is what we want. So as you can see, this will result in a better approximation of the area under the curve from kt minus t to kt. And so all we need to do is find the area of the trapezoid. So the area of the trapezoid is a plus b divided by 2 times the width or the height. In this case it would be t. So the formula for area is a plus b divided by 2, so which is e of kt minus t plus e of kt divided by 2 times the height or this width, which is basically t, so times t. Now let me put a square bracket around it. So basically the area would be g over 2 times e of k minus 1 plus e of k. So this is what we need to substitute here. So if I bring that here, it would become t over 2 into e of k minus 1 plus e of k. Now if I try to find the z transform of this whole equation, I will get u of z is equal to z inverse u of z plus, so in this case we have t over 2 multiplied to e of k minus 1, and then t, same thing, is multiplied to e of k. So t over 2 z inverse e z plus t over 2 times e z. So basically this will be e of z into t over 2 into z inverse plus 1. So u of z is equals to z inverse u of z plus e of z into t over 2 times z inverse plus 1. Now u z over e z will become t over 2 into z inverse plus 1 divided by 1 minus z inverse, which is equal to t over 2 into 1 plus z divided by z minus 1. And if we further simplify this, we will get t over 2 z plus 1 and 2 into z minus 1. So this is now equivalent to 1 over s. So 1 over s is equivalent to t over 2 times z plus 1 divided by z minus 1. And so s will be equivalent to 2 z minus 1 divided by t z plus 1. So if we go back to my notes, then that's exactly what we see here. So we can simplify this. 1 over s is equivalent to t z plus 1 divided by 2 z minus 1. So s will be equivalent to 2 z minus 1 over t z plus 1. So that is exactly what we got in my result. 2z minus 1 over t z plus 1. S, which is equivalent to 2 z minus 1 over t times z plus 1 into my original equation, which was h of s is equal to, so this was h of s is equals to a over s plus a. So in place of s, we can substitute either the forward rule, the backward rule. So forward rule was s is equivalent to 2z minus 1 over t. Backward rule, s is equivalent to z minus 1 over tz. And trapezoidal rule, s is equal to 2 into z minus 1 divided by t times z plus 1. So we can substitute in place of s those quantities, and our h of s becomes h in terms of z using those three rules. So forward, backward, and trapezoidal rule. Now the trapezoidal rule substitution is also known as Tustin's method, and the transformation is called bilinear transformation. So using trapezoidal rule, as we have seen, trapezoidal rule, using a trapezoid, we can approximate the area under the curve quite accurately. And so this is one of the widely used methods, trapezoidal rule. So this is known as Tustin's method. If we substitute the trapezoidal rule, which is s is 2 times z minus 1 over t into z plus 1 into our h of s equation, then that's known as Tuskin's method. And this whole transformation is called bilinear transformation. So that's on numerical integration methods of converting a continuous system to a discrete system.